Hello, this is Miss Moore, and today during chemistry, we're going to learn how to do gas stoichiometry. Today's essential question: how can stoichiometry and the gas laws be combined to determine amounts of products or reactants? Before proceeding with today's lecture, please make sure you have available your reference tables and your calculators. All right, so to learn how to do gas stoichiometry, we are going to do gas stoichiometry. I think that's the best way to learn this stuff. All right, so we're going to do a practice problem. The question is, if the combustion of ethanol produces 98.2 milliliters of water measured at 2.26 atm and 40 degrees Celsius, what volume of CO2 is produced when measured at STP? So before we proceed, let me give you a warning. These problems are not just plug and chug. Okay, you're going to have to think, you're going to have to really look at the problem, really look at what's given, really look at what they're asking for, and then use your knowledge of both gas laws and stoichiometry to come up with a way to answer the question. All right, so I think what I would do is figure out what our known and our unknown is and make a list of everything we know about the known and we know about the unknown. So it looks like we're starting with water. All right, what we know about water is that we're going to end up, when you combust ethanol, that we end up with 98.2 milliliters of water. We know the pressure that this happened at and the temperature. So I'm going to jot that information down really quickly. So for water, we know the volume is 98.2 milliliters. We know the pressure is 2.26 atm. And we know the temperature is 40 degrees Celsius, but we know, since we're using gas laws, we're going to have to change this to Kelvin. So it's going to be 40 plus 273.15, giving us 313.15. We should check sig figs really quickly because we just did a calculation. And since we're adding, we look at the decimal places. So we have 40.0. And then we had 273.15, so we're going to end up with one digit after the decimal. So let's change this to 313.2. Okay. So now we have listed what we know about the known. Let's look about what we know about the unknown. We're asking a question about CO2, right? The volume of CO2. So we have CO2. We know about its volume. We know that it's our X, right? We also know the temperature and the pressure. So our pressure is 1.00 atm. And our temperature is 273.15 K. So now that we know all this information, is there a way, with everything we know, to calculate volume of CO2? We can't use Charles Boyle's Gay-Lussac, any of those, because we only have one of each pressure or temperature for each of our compounds, water, carbon dioxide. We also can't use the ideal gas law, at least for CO2, because we don't know N, right? And we don't know X. But for H2O, we could use the ideal gas law, making our N X, right? And what would that do for us? Well, if we know the number of moles of water, we can then use stoichiometry, right, to figure out the moles of carbon dioxide. So let's try that. So we need an R here. And our unit is in atm, which means we need to use 0.08206 liters atm. Mole. Okay. Also, we need to change our volume. Right now, our volume is milliliters, which is not going to work. So we need to make this liters, which would make it 0.0982 liters. All right, from here we can just plug this stuff in to the ideal gas law, giving us, which remember is PV equals NR and T. So we have a pressure of 2.26 atm. We have a volume of 0.0982 liters. N is our X. We have an R of 0.08206 liters atm. Mol K, and a temperature of 313.2 K. Okay, we can cross out K. We can't cross out the moles, but what we can do is multiply moles on both sides, crossing those out. And now let's just solve for X. And solving for X, I got 0.00863,508, etc. mole. And if we look at our sig figs, we have 3 and 3 and 4, and the R1 doesn't count, so 3 right there. So now let's put this in our list of knowns. So now we know that we have, for moles of H2O, produced 0.00864 mole. So now we know the number of moles of water, but that doesn't help us much yet. It doesn't give us our answer, right? Because we wanted the volume of CO2. However, gets rid of this for now. Look what we have. We have a balanced equation. We can take the number of moles of water, 0.00864 mole H2O, and we can use our balanced equation as a conversion factor to figure out the number of moles of CO2. Then we'll have enough information for moles of CO2 to figure out the liters of CO2. So we're interested in water, which is 3 moles, and CO2, which is 2 moles. So we'll have 3 moles of water on the bottom so that our units can cancel out, and 2 moles of carbon dioxide on the top. So now we can calculate the number of moles of carbon dioxide. And I got 0.00576 moles of carbon dioxide. So we can put that into our list of what we know about our unknown. We know we have 0.00576 mole of CO2. And now we can use the ideal gas law to calculate mass, or no, sorry, not mass, volume of CO2. All right, so we have enough information now. All we need to do is figure out our R, and we're going to use the same R as last time, 0.08206 liters atm mol K, and now we can calculate volume. Let me get rid of the H2O information so we have enough space to work. All right, so ideal gas law again is PV equals NR T, and we just need to plug in the information that we have here. So our pressure is 1.00 atm. We don't know the volume. N is 0.00576 mole. And R, looks like I need to move this stuff over a little bit to make some room. R is 0.08206 liters ATM over mole. Okay, and our temperature is 273 K. So our moles cross out, our K's cross out, and now we can solve for X. So we'll have 1.00 ATM X equals 0.129108 etc. liters ATM. Divide both sides by 1 ATM, giving us 0.129108 etc. liters. And our sig figs, constant, we don't need to worry about it. Constant, we don't need to worry about it. 3 and constant. So 3 sig figs. So the final answer is 0.129 liters of CO2. So back to our original question. When the combustion of ethanol produces 98.2 milliliters of water, we end up with 0.129 liters of CO2, or if we want to stay consistent, it would be 129 milliliters of CO2. Okay, so there's an example of using both the ideal gas law and stoichiometry to come up with a variable. As you can see, it's just thinking, planning. There you go. All right, let's try one more practice problem. This is going to be different than the other practice problem. That's the thing about gas stoichiometry. Every problem is different. If possible, try to hit pause and see if you can come up with your own plan. If not, just follow along. All right, so our question is, if we have 15.3 grams of sodium and it reacts with excess water, which means there's plenty of water, what volume of hydrogen at STP is formed? All right, so I'm going to start by making my list of what I know and what I don't know. All right, so our known definitely has to be sodium because we know we have 15.3 grams of that. So I have sodium, and I know the mass equals 15.3 grams. Goodness, that's about all I know about sodium. So let's look at hydrogen. Hydrogen, it's asking us for the volume. So we know our volume is X. We know that the pressure is 1 atm. We know that because of this STP. And we know the temperature is 273.15 K. All right, so it looks like we're going to be needing to use the ideal gas law again. However, we don't know N. So somehow, with our known of sodium, we need to end up with moles of hydrogen. So I think this is another stoichiometry problem. We could have our math problem, if you want to look at it that way, is that we have 15.3 grams of sodium equals X, we need moles, right? X moles of hydrogen. So how do we go about doing that? Well, we can start with 15.3 grams of sodium. And to convert from grams of sodium to moles of sodium, we can use 1 mole of sodium equals the molar mass of sodium. So we're going to have 22.99 grams of sodium, 1 mole of sodium. So those cross out. Now that we're at moles of sodium, we can use the balanced equation to get to moles of hydrogen. So we are interested in sodium, which is 2 moles, and hydrogen, which is 1 mole. So we're going to have 2 moles of sodium, 1 mole of hydrogen. Those cross out, and now we can solve for moles of hydrogen. And I got 0.33275, etc. mole H2. And looking at sig figs, well, the only sig fig we need to look at is that one, well, and this one. So 3 sig figs. So our number of moles of hydrogen gas is 0.333 moles. Now we have enough information to actually solve for our original question, which is what volume of hydrogen is formed. So we need to put in our R, and then we can use the ideal gas law. And because our pressure is in ATM, we'll be using the 0.08206 liter ATM mole K. Okay, so let's plug this information into the ideal gas law, and we've got our answer. So ideal gas law. So our pressure is 1.00 ATM. Our volume is what we don't know. N is our number of moles, 0.333 mole, times the R, which is 0.8206 liter ATM mole K, and our temperature is 273.15 K. All right, so we can cross out K and mole, and when we go to solve, we end up with 1.00 ATM X equals 7.464091, etc. liters ATM. Divide both sides by 1 ATM. And we end up with this right here. And now we just need to figure out sig figs. So constant, solved for constant, so 3 sig figs. So the final answer is 7.46 liters of H2. There you go. So again, solving these problems, you need to look at what you've got, come up with a plan, and go for it. All right, folks, that's it for today. Have a good one.